celebrating Thieme Chemistry's Best Paper awardees. You can see them here on this slide, and I will be introducing them individually later on when they give their presentations. But before we start, I'd like to introduce myself. I'm Jean Andres, and I'm the executive publisher of the journals Synthesis, Synlet, Synfax, and Synopen. I joined Thieme fairly recently, just over 7 months ago, but I have more than 12 years of experience in science publishing. I also have a bit of a background as an academic in a university prior to obtaining my PhD in chemical engineering at the University of Cambridge. And I'm very, very delighted to be here with you today for this seminar. And I'm looking forward to the great talks that we will be hearing from our speakers. To start with, some housekeeping items. Please do note that this seminar is being recorded and that for continuity and simplicity, participants' microphones will remain muted throughout. We do invite and very much encourage you, however, to please use the Q&A window to ask questions, as there will be time for these following each presentation, during which our speakers will respond to as many questions as possible from the chat. We also invite you to join the conversation online via LinkedIn by perhaps sharing your thoughts and takeaways from the seminar. And please also subscribe to our seminar series so that you are kept updated on all the great webinars we are offering for the rest of the year and beyond. And please connect with us by subscribing to our newsletter as well. My colleague, Dr. Ilya Sharonov, has also shared these links in the chat, so please find them there. So please allow me to first introduce you to Thieme in case you have not heard about us before. Thieme is a company based in Germany, but as you can see here, we have a significant presence worldwide, including offices in New York, Delhi, Rio de Janeiro, Beijing, and London. And we have over 130 years of experience in publishing science and medical information. These are our products, our journals and e-products. You might already know about Science of Synthesis, which is a full text resource for methods in synthetic organic chemistry. As I mentioned, I am the executive publisher for our organic chemistry journals, which include Synthesis, Synlet, Synfax, Synopen, organic materials as well. And we also have a suite of biomedical chemistry journals, including drug research, planta medica, and pharmacopsychiatry. We have sustainability and circularity now as well, and our pharmaceutical substances online knowledge base for API synthesis patents and applications. We are here to celebrate our Best Paper Awards, and we'd like to let everybody know that when you publish in Synthesis, Synlet, Synopen, and organic materials, you can automatically qualify to be considered for the awards. And these are the criteria that we look for when we are looking for the Best Paper Award for the year for the journals. We should have new methods, significant improvements of existing methods, or an application of synthetic methods to large-scale production or new bond-forming reactions. And there's a prize money involved and certificate, and prize winners are selected early in the year based on the previous year's publications, and we announced them in January. Just a few more details about our journals. Synthesis is our review and full paper journal. We publish 24 issues a year. We provide dependable research results with detailed experimental procedures and full characterization of all important new products, as well as scientific primary data. And you can see here our editorial board, which is a very well-respected and very internationally diverse group of prominent scientists. they take care of the peer review process for the journal. And SynLet is our international letters journal, publishing 20 issues a year. And you can see here our editorial board members as well. Just like Synthesis, we have our fast and secure and very rigorous select crowd review as an option to traditional peer review as well. It's a very innovative kind of peer review. And we'd like to invite you to try it if you haven't already. I wanted to let you know about this newish journal in our family. I think it's been, well, compared with Synthesis and Synlet. Sustainability and Circularity Now is one of our exciting journals. It's an open access journals, and it will broadcast challenges and revolutionary solutions for a sustainable future. And the editor-in-chief is Chris Sluvek. And if you would like to submit your work, if it is in the scope of sustainability and circularity now, please do. It has a very broad scope, so I'm sure that it will be very very flexible and very interesting for many of you. So that's it from me. On that note, I'd like to thank you for your attention so far, and we will now proceed with our talks without further ado. I will stop sharing my screen. Now, we would like to start with our first presentation today. We are going to start with the winner of the SynLet Best Paper Award, and that is Professor Sung-Kyu Han. Professor Sung-Kyu Han is based at the Korea Advanced Institute of Science and Technology in South Korea. He received his BS degree in chemistry from KAIST in 2006, and he earned his PhD in chemistry from MIT in 2012 under the guidance of Professor Mohamed Movasagi. He then conducted postdoctoral research at Yale University with Professor Scott J. Miller until 2014. In July 2014, he joined the Department of Chemistry at KAIST as an assistant professor, and he's now currently a full professor. His group focuses on natural product synthesis, natural products-inspired method development, and natural products-based drug discovery. Professor Han has received several awards, including the Hansung Science Prize, the KCS Wiley Young Chemist Award, and the Young Scientist Award. Internationally, he was honored with the Thieme Chemistry Journals Award in 2018, and as I mentioned, the SynLet Best Paper Award for 2024. So I'd like to hand over now to Professor Han for his presentation.
Thank you, Dr. Andres, for the very nice introduction. And yes, thank you. And I'm greatly honored to receive the prestigious SynLet Best Paper Award 2024, and it is my great pleasure to present. So for that, I greatly appreciate Thieme for that award, and it is my great pleasure to to present some of our group's recent discovery in the field of security alkaloids. Yeah, the specific family of natural product that I'm going to present today is securinic alkaloids. This is the structure of securinin. It consists of this tetracyclic structure with interesting stereochemistry, 3 stereogenic center. And the first isolation of securinin was in 1956. And since then, over 100 securinic alkaloid has been isolated so far. It is known to be a specific GABA receptor. And also in Asian country, this has been used as a traditional medicine. The plant extract has been used as a traditional medicine, and it is reported to have numerous interesting biological activity and also structurally very beautiful, and it attracted the interest of many famous and also well-renowned synthetic organic chemists worldwide. But also I have to highlight that over 35 photosynthesis, historically the focus in the field of security alkaloid synthesis was on the construction of this tetracyclic core. But when I started my independent career at KAIS in 2014, now almost 11 years ago, I decided to focus or to turn our interests to the more complex security alkaloid biosynthetic offspring that are biosynthesized via oxidation and dimerization, showing this greater complexity, structural complexity. They're also not only structurally complex, but they are known to upregulate eukaryotic elongation factor 2 mediated protein synthesis, which phenotypically they show that they can induce neuronal differentiation and neurite extension. And this kind of neuroplasticity inducing effect can have an impact on treatment of neurodegenerative disorder and drug addiction. So that's how we got interested to the super complex security alkaloid. So now if you look at the structure of the monomer secondary framework, you can see that on the right side from this view, it contains this alpha, beta, gamma, delta unsaturated ester moiety. And because of that, this is a Michael acceptor. And because of this, they can act, it can undergo, so to speak, the Rao-Currier type dimerization. And we actually were able to synthesize various type of dimetic Rao-Currier reaction-based security alkaloids. But because of the interest of time, I'm not going to focus on that. What I want to focus on is from this view, the left side, which contained this N-containing heterocyclic structure, in this case, piperidine with tertiary amine moiety. Because I guess one of the most notable reactivity of the tertiary amine is it can undergo oxidation to form the N oxide. And if you further oxidize the N oxide, you can form the nitron. And nitron with an alkene can undergo 3+2 cycloaddition reaction. And if that happens intramolecularly, virosine A and B could be formed, and actually synthesis based on that reactivity has been reported. Or intermolecularly, you can see here, this isoxazoline ring can be formed via intermolecular 3+2 cycloaddition between nitron and an alkene moiety shown here. So, and also 1-to-Meisenheimer rearrangement, which is a reactivity that I'm going to detail more in after a few slides in my talk. So that was also known to form this alkoxyamine moiety shown here. But one of the kind of elusive structural motif was, so if this alkoxyamine moiety can undergo basically deprotonation, elimination, and if we can somehow induce the dehydrogenation at 2,3 position, then we envision that there are so many natural products that we thought are biogenetically, biosynthetically deriving, stemming from this 2,3 dehydroallosecurinine moiety. And our focus was on actually accessing this intermediate and further derivatize this to this more complex congener of secondary alkaloids. So now we can think that, oh, after forming this N oxide moiety, usually the name reaction that will come up to your mind is Polonovsky reaction, which is activating this N oxide and inducing elimination reaction. So in order to get the dehydrogenation at 2,3 position, we need to deprotonate at the C2 position. But whenever we subjected this N oxide intermediate with conventional Polonovsky reaction, which is trifluoroacetic anhydride, we always observe deprotonation at C6 position, enamine formation, and further reaction with 3-FAA to get this trifluoroacylated enamine derivative. And the reasoning behind that can be rationalized by the fact that I just mentioned a conventional Polonovsky reaction. This is the leaving group, and it operates via E2 elimination. So the proton that is anti-periplanar to the leaving group will be deprotonated. And in this system, the only proton that is anti-periplanar to leaving group is residing at C6 position. That's why we are always getting deprotonation at C6 position and not at the C2 position. So in order to circumvent this problem, to solve this problem, what we needed is not E2 elimination, but EI elimination in a syn fashion. So we needed a way to not only activate, but at the same time, deprotonate via this the syn pathway, EI elimination pathway. And after a lot of experimentation, we found out that upon treatment with this N oxide intermediate with vanadium ACAC, we can not only activate, but also deprotonate intramolecularly. internally, intramolecularly, to induce the C2 deprotonation, which formed the C2 iminium ion, and after tautomerization, we were able to get this 2,3-dihydroallosecurin. This is discovery by Dr. Kyumin Gang. So once we have accessed this 2,3, so to speak, so 2,3-dihydroallosecurenin, then we could explore its reactivity. One example is the synthesis of sequamamine A, which is studied with DMDO oxidation of this enamine moiety with oxidation, and then upon BF3 etherate treatment, we could open up the epoxide to form this iminium ion, and then we in situ reduced it with sodium cyanide borohydride to get 3-hydroxyallosecurenin compound. We treat that with trifluoroacetonhydride, TAD-MAP, to trifluoroacetylate. And what happened is this nitrogen induced formed this underwent intramolecular SN2 reaction to form this aziridinium intermediate, which upon reaction with trifluoroacetate underwent 1,2 amine shift, and upon methanolysis of trifluoroacetate group, we're able to secure the synthetic sample of sequamamine A. Not only that, like this 2,3-dihydroallosecurenin, we could also undergo methylylation using this TMS substituting methylyl iodide in the presence of silver carbonate. We could undergo this methylylation reaction. And we treated this enamine compound with MBS. The MBS bromonium ion formation occurred from the bottom phase and the top phase to give 2-diastereomeric intermediate. But then if you focus in here, and once after the bromonium was opened up by the nitrogen lone pair, you have this iminium ion, and this could undergo intramolecular azasaccharide reaction to form this carbon-carbon bond. And this double bond, after forming amine salt with TFA, we could oxidatively cleave the double bond to generate this ketone. And upon treatment with silica gel, we could induce beta bromide elimination to access the first synthetic sample of fluorouracil A. With the other diastereomer, we basically repeated the same reaction sequence. So we could oxidative cleave here. And upon silica gel treatment, we expected to get this 2-epifluorouracil A, but we observed that as soon as it formed simultaneously, it underwent this 1,2 amine shift to give the structure, which is actually the structure of fluorouracil A. So actually, fluorouracil A and fluorouracil B were reported in the same isolation paper with this kind of different molecular framework, but we discovered that actually the reasoning behind this molecular framework is what determined this 1,2 amine shift is the stereochemistry at the C2 position, governs the fate of 1,2 amine shift, and probably the discovery of this chemical reactivity might be related to actual biosynthesis of these two natural products. So and also allosecurenin, well, what we can do is an oxidation, as I mentioned, 1,2-Meisenheimer rearrangement that will give philantidin, which is also a natural product. And as I mentioned, using our regioselective Polonovsky reaction, we can get to this compound, 2,3-dihydroallosecurenin, and which in the presence of singlet oxygen, we can oxidatively cleave this 2,3 C2C3 double bond to form this aldehyde. In the presence of methanol, we also can induce 1,6 conjugate addition of the methoxy group, so we can get to this compound. And if you look at this is the structure of fluorouracil B, and we can access philantidin and this aldehyde. So if you look at the structure, the only thing we should do is somehow, if we can remove the hydrogen H2 and form this carbon-carbon bond between this carbon and this carbon, that basically constitute the fluorouracil B, and that will be the simply disconnection. So meaning that if we can do the cross dehydrogenative coupling reaction between this aldehyde and somehow this electron withdrawing electron deficient olefin, we might be able to access fluorouracil B in very concise and very streamlined method. The problem with that is this is the aldehyde. Now we need to form this carbon-carbon bond in a cross dehydrogenative coupling reaction, CDC reaction. And this is a cross electrophile reaction, so probably it need to be oxidative. So and this is react in two electron realm. This is mismatch. This is electrophile. So you cannot form a carbon-carbon bond between two electrophile. But the moment if we switch the paradigm to radical chemistry, so if we can induce hydrogen abstraction and form the acyl radical, now this acyl radical becomes nucleophilic radical, which would be able via GZ addition to the electron deficient olefin to form the desired carbon-carbon bond. Now, but here the second problem can be arose, and the problem is, as you can see here, the redox potential of the product 1.5 volt, and that of the starting material is 0.2 volt. And we, as I mentioned before, we probably will have to run this reaction under oxidative condition. And in the presence of the active oxidizing species, the acyl radical itself would be more prone to oxidation. So the way to solve this problem is the active oxidizing species, the species that can actually oxidize the acyl radical should be, if we have to keep that species in a catalytic amount, a smaller amount, because if we can keep that suppression catalytic concentration control, then our substrate will exist as a stoichiometric amount, so we can win that kinetic battle. So that was our the strategy. Now the final problem is, we have to oxidize this radical in order to get to this desired the enone compound, but this one is very difficult to oxidize. Actually, forming a carbocation intermediate right next to electron withdrawing group is energetically going very uphill. And our solution to that is going roundabout to do the halide transfer first, and then E1CB elimination that would give the same product. So we decided to take that strategy. So yeah, to make a long story short, after a lot of studies and investigation, especially by Dr. Thieme Chemistry, who worked on this project single-handedly, so he discovered that the copper daptochloride, the copper-based photocatalyst in the presence of TBEC, the oxidant, and quinoklidine salt, upon irradiation of 525 nanometer green light, were able to induce the desired carbon-carbon bond formation, the CDC reaction. The reaction mechanism involved the activation of copper-1 species to the activated copper-1 species, which now will reduce the oxygen-oxygen bond of the TBC oxidant to generate TB-toxic radical. And this TB-toxic radical will induce hydrogen atom transfer from the aldehyde substrate to generate the acyl radical. And this acyl radical will undergo GZ addition to form the desired carbon-carbon bond. And at this point, the radical can go halide transfer from copper-2 chloride species to generate the beta-chlorinated compound and the copper-1, the alkoxy intermediate, and which can undergo ligand exchange with quinoklidine HCl salt to regenerate the active the catalytic species and liberate quinoklidine, which is the base that will induce the E1CB elimination from this beta-chloroketone compound to generate the compound. So also one note that I want to make, under optimized condition, you can see we utilize 0.05 more% of the catalyst. But when we use, for example, 0.5 more%, so usually more catalyst can boost up the reactivity. But in this case, when we utilize more catalyst, for example, 0.5 more%, we observe more of the ester compound, which is originating from the oxidation of this acyl radical intermediate. So consistent with our hypothesis that acyl radical is very facile, can be very easily oxidized, and we needed we had to reduce the amount of catalyst used to get more desired product. So, and also, so another interesting type of natural product in this, another natural product in this family was, as I mentioned, upon N-oxidation, many different type of alkoxyamine-based natural secondary alkali have been reported, and they all contain, as you can see here, different type of oxygen and carbon connectivity. Here, the oxygen is connected to the beta carbon. Here, the oxygen is connected to the gamma carbon. Here, to epsilon carbon. Here's the gamma carbon. So we were interested what would be the chemical reactivity that was responsible for this interesting connectivity and topology of the molecule, these fascinating molecules. And we first decided to tackle cyclogen A and cycloamine D. Our synthesis commenced with asymmetric conjugate modulation developed by Professor Chae-Suk Yoon and Seongkyungwan University from Korea, and then we oxidize it to get the C4 hydroxy in a selective manner. After methylation, we treat the desired Bach-protected lactam with superhydride to generate this hemiaminal moiety. And today I'm not going to detail the large-scale synthesis of this TBDPS-protected many-staurolide, but we developed a decagram scale synthesis of this intermediate. And upon triplet triethylamine, the reagent, we were able to form this diinosylic ether, which in the presence of dibutyl boron triplet, the Lewis acid, it induced this carbon-carbon bond formation via Mannig reaction. So this stereochemistry is determined by, basically the iminoamine is approaching from the opposite side of OTBTPS group, and this stereochemistry is determined by first Platoner rule, which determine this stereochemistry. So after Bach deprotection, TFA-mediated Bach deprotection and triethylamine treatment, we could induce the intramolecular 1,6 conjugate addition to form this norsecutinane framework of the natural product. So, and upon treatment with methyl chloride, which is one of the strategies that has been widely used in the security alkaloid synthesis community, we could induce the three-member intermediate, as I mentioned before. And then after E1CB elimination, we could induce this 1,2-amine shift to generate securitinine. And here, let me explain the 1,2-Meisenheimer rearrangement that appears several times from my talk today. So after N-oxidation, we get this N-oxide compound. And this N-oxide compound can undergo homolytic cleavage between this nitrogen and carbon bond, because the resulting two radical is relatively stable nitroxyl radical and allylic radical, which can undergo recombination to form this oxygen carbon bond, and that constitutes the saccharoamine D. That's the 1,2-Meisenheimer rearrangement. Interestingly, when we subjected the same the compound with this precursor to securitinine to the same reaction condition, MCPBA, the N-oxidation occur, but instead now we don't have the incentive to do any homolytic cleavage here. Instead, it underwent COP elimination to form the hydroxylamine moiety, which underwent a spontaneous 1,4 conjugate addition to this butenolide moiety to constitute, to complete the first synthesis of securinin A, the first order synthesis of securinin A. So actually, in the same the paper, we also were able to access this tertiary tricyclic intermediate, which after TBDPS deprotection and Bach deprotection, we're able to get this tetracyclic structure. And actually, this is the SynLab paper award paper described in the SynLab paper. Our goal was to make this 4-alpha hydroxy allosecurinin and securinin F. Now, the critical the step here was we needed to actually epimerize the C2 position here. As you can see here, this is opposite configuration, and also the C4 position. And this is around the time that Professor John Ellman from Yale University, he reported this very beautiful light-mediated hydrogen atom transfer-based epimerization of piperidines. So it reported that this stereogenic center can be inverted. And the mechanism of this of his transformation was in the presence of iridium catalyst and thiol. The thiol can be deprotonated to the present tertiary amine. Thiolate can undergo oxidation to generate the thiol radical, and thiol radical is known to induce hydrogen atom transfer very reversibly. So that basically abstracted the most plausible hydrogen with the lowest bond dissociation energy, which is the alpha to the nitrogen compound, to generate this radical. And because this HAT is reversible, basically you can set thermodynamic equilibrium, and the most energetically stable the compound, right, will be able to form by establishing the thermodynamic equilibrium. So we subjected our compound to the Ellman condition, and we were happy to observe that actually, so we were able to establish the thermodynamic equilibrium. And as you can see here, the hydroxyl group is pointing axial, hydroxyl group is pointing equatorial, and the A value of hydroxyl group is about 0.87 kcal per mole, which at room temperature correspond to the equilibrium constant of 0.23, and that is actually 72% yield, is very consistent with the A value shown here. So we were able to get this. The rest of the mass is the starting material, which is the result of this equilibrium. And once we were able to successfully epimerize the C2 position, now we conducted a double, so here double activation of this hydroxyl with this hydroxyl group under Mitsunobu reaction condition. So in this case, we were able to went to amine shift. In this case, it underwent a Mitsunobu reaction with 4-nitrobenzoic acid, which upon meta-analysis, we're able to invert the stereochemistry to get 4-alpha hydroxy aldosylcysteine, and upon oxidation and 1,2-Meisenheimer rearrangement, we're able to get the first synthetic sample of second engine F, which we published in SynLet. So now, we solved this problem: oxygen epsilon carbon bond formation and oxygen beta carbon bond formation. We're interested in what about the oxygen gamma carbon bond formation? Because we obtain a lot of confidence by making both this compound and this compound. We're confident that we will be able to also access this oxygen gamma bond formation, which is the constitutive framework of second engine B. So our initial hypothesis for this for accessing second engine B was, because we can access second engine A, well, we are going to do beta elimination to generate this hydroxylamine. And if this hydroxylamine can somehow undergo SN2 prime O alkylation by relieving this leaving group activated hydroxyl group and double bond here, that basically will constitute second engine B. That's how we can access that. So that was our initial hypothesis. So we activated the allylic hydroxyl group with methyl chloride, and then we treated this compound with DBU, which successfully induced the beta elimination. But the hydroxylamine, instead of undergoing desired SN2 prime condition reaction, it underwent direct SN2 reaction to form this oxygen carbon bond, epsilon carbon bond, which is cycloamine D. Out of desperation, so we worked on this for a couple of years. Out of desperation, we inverted the stereochemistry here to prevent the SN2 reaction, but still, probably via SN1 reaction, we were still getting this direct O alkylation or the nucleophilic substitution reaction to access cycloamine D. And so this was our desired second engine B. This was what we were getting. But structurally, cycloamine D contains this alpha, beta, gamma, delta fully saturated compound, which is thermodynamically more stable. On the other hand, the second engine B contains these two dienes are skip dienes, so they are not in conjugation. So naturally, thermodynamic probably less stable. So we were trying to make this contra thermodynamic product, but we were always getting the thermodynamic product. So that was our dilemma. But this was around this time that we actually encounter a reference saying that in the presence of chromophore and this alkoxyamine, the chromophore can get on the photochemical excitation to the triplet state. We can treat that as a diradical, and by doing that, we can actually induce this oxygen carbon homolytic cleavage, similar to the mechanism of 1,2-Meisenheimer rearrangement to generate this nitroxyl radical and this benzylic radical. In this paper by Gilinov, they were utilizing this benzylic radical for their surface patterning. But in our case, we thought that, maybe because we have this fully conjugated alpha, beta, gamma, delta unsaturated ester moiety, that we were expecting that it would be a better chromophore than just alpha, beta unsaturated ester. So this might get photoexcitation, and upon photoexcitation to the similar mechanism shown above, that probably we can induce this oxygen carbon homolytic cleavage to generate this radical, allylic radical, and nitroxyl radical. And one thing that can happen probably once we access this intermediate is the oxygen epsilon carbon bond formation again, which will go back to cycloamine D. But this under irradiation will probably get excited again. So this we can we can have this intermediate. And once in a while, if the oxygen form an oxygen carbon bond with this gamma carbon, then that's this bond, and that's basically the way that we anticipated the formation of second engine B can happen. And once we have this carbon oxygen bond, then we don't anymore have this fully conjugated system. We only have the alpha beta, the lacto moiety, alpha beta unsaturated lacto moiety, and we thought that it would be more difficult to excite this less conjugated system. And actually, so a thing that never worked for over thermal condition for over a couple of years, the moment we added blue light in the presence of photosensitizers such as thioxanthin, we're able to immediately convert cycloamine D to second engine B in very high yield. So when we were using more lower wavelengths, so 370 nanometer LED, we didn't need the photosynthesizer. And actually when R is a methoxy, that's the natural product, but the absent when R was H. So the presence of methoxy didn't much affect this rearrangement. And actually the structural section engine build could be unambiguously conformed by a single crystal X-ray diffraction analysis. So also one interesting observation that we made is that if we hit this rearranged compound product under heat, like 130%, 30 degrees Celsius degree, it went back to the thermodynamically more stable compound. So some DFT calculation of this transformation was conducted. I want to point out that actually the calculated triplet excited state energy of the substrate, fully conjugated substrate, was 53.51. On the other hand, that of the rearranged product with the skipped ion moiety was 76.23, consistent with the hypothesis. So this one is more difficult to excite. This one is easier to excite. And once excited, it goes to this product. Or thermodynamically, we can also thermally we can somehow force the cleavage of this oxygen-carbon bond, and in that case, we are forming the thermodynamically more stable compound shown here, and that explains all the observation. So after making that observation, we thought, so what about if we attach an electron donating group at the alpha, beta, gamma, delta position of this phelantidine, for example? What we expected to happen is intermolecular charge transfer, and which will establish push-pull system, and we expected the homolumo gap would decrease, and we might be able to observe a visible light. So in the absence of electron donating group, the compound will be colorless. The phelantidine will be colorless, but the moment we add electron donating group, it will be colorful, and upon this rearrangement, that will be colorless. So we thought we might be able to design a photochromic material. And actually, so I'm mentioning here, actually, I showed many chemistry utilizing allosecurine in a starting material. So in our lab, we extract this compound allosecurine, which is a major component in Flugelso fruticosa, which is a plant that is ubiquitous in Asian countries, especially also in Korea. So from 2 kilograms of the root, we can secure about 11 grams of this allosecurine. And in this case, after, as I mentioned, 1,2 Mesenheimer oxidation and 1,2 Mesenheimer rearrangement, we can get phelantidine, which is colorless. And via a Heck reaction of this, once we attach this dimethyl aniline derivative, like electron donating group, this turned yellow, consistent with the hypothesis that now the homolumo gap is decreased. So, and actually now with this dimethyl aniline moiety, we don't even need the photosynthesizer and UV light. With just in 427 nanometer with very high conversion, we could convert to the rearranged product B shown here, which was colorless. And this compound, because itself contains this chromophore at 310 nanometers, so with a stronger, shorter wavelength light, UV light, we could actually establish a photostationary state, which showed the existence A and B 93:7 ratio. So actually, the reason why we are getting these two very separate photostationary state is that you can see that at 427 nanometer and at 310 nanometer, the AB is the maximum of absorbance is very well separated. That's why we're able to get very high, well separated photostationary state in these two distinct wavelengths. And also, the system showed a reasonable fatigue resistance. We could repeat this process without much of degradation of the compound. Also, the Arrhenius plot showed that the thermal half-life of the rearranged product at room temperature is about 57 days. And our TGA analysis estimated that compound A is stable up to the composition initiated 220 degrees. So this is pretty stable compound. Also, one thing that we did, we dispersed this material to polydimethyl siloxane, which is a hydrogel. So polymeric hydrogel. This compound is yellow. And the moment we masked this material, this jelly material with the Keist, and if we irradiate with 427 nanometer, only the part that is irradiated is turned yet colorless. And also we observed that this material was also fluorescent, while the rearranged compound is not fluorescent. So this is also fluorescent on-off kind of material, photoswitch material. And if we irradiate the whole part with 427 nanometer, we can completely delete. Or now if we use the same mask and irradiate with 310 nanometer, now we can write in yellow, which is this compound, is we see the conversion to that compound, and we can erase. So this one is kind of interesting application. So natural product inspired or based new type of molecular photoswitch. So what I've shown you today is, so what our group we contributed to the field is starting from this monometric, very basic monometric secondary unit, we were able to actually form or oxidize and dimerize and form many interesting natural products. So I only have a few examples today, but we have also many other examples. And this work couldn't have been done with all of the effort of my group members, so I'm greatly indebted to all my group member, and also, yeah, I want to thank the Thieme again for giving me this opportunity and the honorable prize. Thank you.
Thank you so much, Professor Han. That was such a fascinating presentation. And we appreciate how much you explain things to us. I would like to hand over to my colleague, Dr. Ilya Sharanov, who will moderate the questions. I think we have one question in the chat. Ilya?
Yes, thank you, Professor Han. It was a fantastic talk. It was very interesting to see all the progress that you made. And we have one question in the chat is, did you calculate the triplet states experimentally? From Christian.
Oh, no, not experimentally. Yeah, we just do the DFT calculation to get the compound. But currently what we are doing is in collaboration with physical chemists, we are actually doing femtosecond transient absorption spectroscopy to actually capture the dynamics of this very interesting radical system. So we are doing more experiment, but the triple excited energy is based on the calculation.
Okay, thank you very much. I think there are no more questions. I have one question from myself. Have you ever tried any other solvents in the spectral, when you were talking about the photo switches? You were doing the absorbance spectral in benzene, right? I'm curious if you tried any other solvents.
We tried several solvents, but the benzene, in terms of solubility and degradation of the material, showed the best performance. So that's why we settled with benzene for this specific.
Understood. Thank you very much.
Yeah.
Okay, then if there are no questions, I once again thank you very much, Professor Han, for this extraordinary talk. And I'm giving the words to Jean.
Thanks, Ilya. Now we go to our Organic Materials Best Paper Award winner. And working with Professor Kay Mullen.
Recording in progress.
As a AC in chemistry. I would like to ask Dr. Freudenberg to now start his presentation.
Yes.
Thank you, Dr. Andres, for this introduction, and also thank you for the opportunity to speak here. Before I start talking about stabilizing soluble azenes and azacenes, I would like to, as an introduction, showcase some of the azine chemistry we are investigating in the group of Uwe Bunz, which also serves as an introduction for the usage of these materials. So the azines and azacenes are interesting materials for organic electronics. Anthracene is a potent emitter. If you increase the backbone of the azine and go to pentazenes and their aza derivative, these become hole and electron semiconductors used for organic field effect transistors. Pentazene and tetrazene are singlet fission chromophores, and some of our work also focuses on the creation of dimers for intramolecular singlet fission. And another property that starts to emerge is that if you increase the backbone of the azine and go to nonacenes, then inherent diradical character starts to emerge. And this is another aspect of our research in Uwe Bunz's lab. But today I would like to stick to the methods of stabilization. And for this, I brought an overview over the longest azenes prepared so far with some recent milestones. And in this map, you can see on the top the unsubstituted azenes synthesized in matrices in bulk on surfaces and as thin films. And you can see that this is a really active field culminating in the synthesis of the pentadicacene by Gottfried and co-workers in 2025. Whereas if you have a look at solution chemistry listed at the bottom here, you can see that after John Anthony's report on his 3 different nonacenes in 2011, no progress has been made with respect to azine length. And the reason for that is that in solution these materials are prone to some decomposition pathways, which involve photooxidation towards the endoperoxides, this 4+4 butterfly type dimerization, and also some Diels-Alder reaction with stabilizing groups that were introduced in order to stabilize the azine backbone. And the reason for these decomposition pathways is simply put by the creation of additional class sextets along the azine backbone, which acts as a thermodynamic driving force. Let's have a look at some highlights regarding soluble azenes in the recent past. And for that purpose, you of course have to start with John Anthony's TIPS pentazene. So pentazene stabilized with triisopropyl ethynyl groups here, which not only is a potent p-type semiconductor, but also this work established the triisopropyl ethynyl groups as the gold standard in stabilizing the higher azenes. John Anthony also prepared the heptazene with a very bulky silyl group, and Professor Woodles and Professor Cheese group tried to improve the stability of these materials. But nevertheless, these materials only live a couple of hours up to, let's say, 2 days in solution, which impedes their use in organic electronics. When it comes to azacenes, I need to mention the tetraaza-pentazene reported by Bunz in 2009, which is the electron deficient pendant towards the TIPS pentazene, and is a superb N-type semiconductor.
Recording in
question, if you do
progress.
that, where to strategically place them and how. And this is the first part of my talk, highlighting some examples from our group. And the first example is also the reason why I was invited here, for which I would like to thank Organic Materials for the recognition, and Thieme, of course. And this project was led by Nico Zeiter, who had a look at the series of azenes going from pentacene to octacene, which are substituted with 4 TIPS ethynyl groups, pairwise spaced with one ring apart on the azene backbones. And in order to synthesize these materials, Nico Zeiter took the commercially available pentacene tetrone and did the addition of the lithiated TIPS ethynyl onto the backbone, then did the subsequent reduction of the tetrol and ended up with around 30% of his 4 TIPS pentacene, which, according to the crystal structure, is able to accommodate the 4 silyl ethynyl groups in this in these positions, but you can learn from the side view that there is some steric strain imposed, which is observable not only by the twisting of the azene backbone, but also by the bending of the alkynes themselves. How to prepare the larger derivatives? The synthesis relies on the generation of an alkyne from this dibromoanthracene species and Diels-Alder reaction with furane. And by creating in situ the arenofuranes and doing another Diels-Alder reaction with diketones of different length, Nico was able to prepare these 3 diketones here, which were again subjected to the addition of TIPS, deprotonated TIPS alkyne, and a reduction with tin dichloride. And from the yields applied here, you can already learn the limit of stabilization for this kind of motifs. Nico was able to isolate hexacene and the heptacene, but not the octacene. And the reason for that is illustrated by the crystal structure obtained from hot pyridine. And upon isolation, not only endoperoxides form, but also this butterfly formal 4+4 type decomposition pathway is active. Nevertheless, with freshly prepared 4 TIPS octacene, you can investigate the optical properties of the series of azenes. And as expected, we observed an bathochromic shift of the azene P band when increasing the azene length about 80 to 90 nanometers for each ring. And in order to get an estimate of the stability, Nico let the compounds age in toluene solution and followed that degradation with UV-Vis spectroscopy, and was able to determine half-life times. And we not only learned that the 4 TIPS ethynyl groups provide a pentacene which is slightly more stable than John Anthony's TIPS pentacene, and also the hexacene is around this has the same order of magnitude of half-life time, but also the heptacene is long-lived enough to make use of this series as active materials in organic electronics, which is rare for the larger azenes. And this was the work of Dr. Hippian, and he not only found that you get ambipolar transport properties for the hexacene and the heptacene, but also he found that the mobility increases with increasing azene length, which we attributed to the decrease in reorganization energy that have been calculated in the literature. Let's make use of this stabilization motif for the aza azenes. This is an example of a persistent diaza azene reported by Bunz in 2014, which is persistent in solution but dimerizes in the solid state. And our idea here was to move the TIPS ethynyl groups more towards the center of the molecules and also investigate the nitrogen content with respect to stability, and also compare it to Nico's derivative, which is the pure hydrocarbon compound, neglecting the silicon in the side groups, of course. And in order to prepare these compounds, Wansheng Zhong did a Buchwald-Hartwig coupling of this anthracene-diamine with the anthracene-dibromate. And honestly, we did not expect it to work or to work that well because of the steric hindrance imposed by the TIPS ethynyl groups. But nevertheless, Dr. Zhong was able to isolate the diazer heptazine 1 in 45% yields after this Buchwald-Hartwig coupling and oxidation. And for comparison reason, he also prepared a regio isomer with an unsubstituted ring between the two sets of TIPS ethynyl groups. In order to increase the nitrogen content, we have to make use of condensation chemistry, as the diaminophenazine is not Buchwald-Hartwig active anymore, so at least in our hands. And by making use of this diodo-dibromo orthoquinone, Wansheng was able to synthesize this tetraazer pentazine here, which could be selectively coupled via a Sonogashira coupling towards this dibromo azer pentazine here. And after Buchwald-Hartwig coupling with phenylene diamine and subsequent oxidation with manganese dioxide, he was able to isolate the tetraazer heptazine in 17% yield, or the hexaazer heptazine in the yield of 6%. The characterization via single crystal structure analysis quickly hinted at the limit of the nitrogen content of the heptazine, because as you can see here, the hexaazer heptazine is contaminated by its dihydroform in the single crystal to at least 50%, which hints at another degradation pathway which takes place if you add too many nitrogens to the azine backbone, which is reduction. And so our learning was that you need a balanced nitrogen content in order to prevent that. Again, after optical characterization, and you can see the expected bathochromic shift of the azer-azine p-band with respect to the hydrocarbon compound here. Wansheng monitored the decay not only by NMR but also by UV vis spectroscopy, and these are these spectral evolutions depicted here. So I brought as an example the decomposition of the diazer heptazine 3, which was the molecule prepared in 2014, compared to the diazer heptazine 1, the regio isomer, which is shielded in the center. And from that, we learned that the diazer heptazine 1, under the same conditions as the other heptazine, hardly decomposes at all, if kept in solution for 7 days. And if you do that series for all of the other compounds, you can deduce an order of stability or a stability ladder. And the diazer heptazine has a half-life time in dilute solution far exceeding 7 days. And a comparison with Nico Zeiter's compound here illustrates that the pyrazine incorporation in the middle greatly benefits the stabilization. And as I said on the last slide, you need a balanced nitrogen content. So if you increase the number of nitrogens on the backbone, then you slightly reduce stability for the tetraazer species and greatly for the hexaazer heptazine. We also investigated another motif, and by that I mean we added more TIPS ethynyl groups onto the backbone of the azine, and this again was a work carried out primarily by Nico Zeiter. And in order to synthesize these 6 TIPS ethynyl substituted heptazine, Nico took a page from Dieter Schlüter's ladder type polymer synthesis, which involves the Diels-Alder addition of this diepoxy anthracene to the tetrazine generating the bisfurane in situ and then doing the Diels-Alder chemistry with the naphthoquinone, furnishing this dioxygenated species here, which was deoxygenated towards the corresponding tetrone, and addition of lithiated TIPS acetylene and a subsequent reduction with tin dichloride furnished two species of heptazine, one which was the tetrabromo derivative and one which was substituted with hydrogen atoms. Here you can see the crystal structures of these compounds together with their degradation times estimated in toluene under ambient conditions. And from that, we learned that the TIPS ethynyl groups in the center of the molecule provide better protection than the bis trifluoromethylphenyl groups used by John Anthony for his nonacines. So that was a message that, or a lesson we learned here. And we also confirmed that the substitution with electron deficient substituents on both sides of the acenes greatly benefits the stability. You might say that these degradation times are boring, and you may be correct because these are measured in very dilute solution. And in order to demonstrate stability, Nikolai Hypien not only constructed again organic field effect transistors, but Nico Zeiter also did some chemistry with the heptazine, which there are not many, if at all, examples of. So he not only reduced the heptazine to the radical anion, the crystal structure is depicted here, he also did the oxidation and even a pi extension reaction with a stannafluorine within acyclic coupling to obtain a tetrabenzononacine. The same synthetic strategy used by Nico can also be extended to the preparation of 4 different nonacines, which he did. And the nonacines he prepared were not only the hydrocarbon or the unsubstituted nonacines, but also substituted with chlorine and bromine atoms or with 4 methoxy groups on the zigzag edge. The crystallization of the unsubstituted nonacine taught us that again, there's some flexibility not only of the alkynes but also of the acene backbone. So out of 4 crystallization attempts, we got 3 different polymorphs. Nico also did the optical characterization, and the position of the p-band matches that of the compound, or roughly matches that of the compound reported by John Anthony. And he did also estimate the half-life times, which range between 5 hours and 9 hours for the series of nonacines, which we believe may be an improvement compared to literature. Again, the bottom gate top contact field effect transistors manufactured by Nikolai brought an improvement of 1 order of magnitude of hole conductivity when compared to the corresponding heptazine. And the group of Professor Dreuf at Heidelberg helped us with the calculations, and they calculated a diradical character for these nonacine, which is roughly half in the Yamaguchi scheme. Let's move away from putting additional TIPS ethynyl groups onto the backbone of the azine, and let's have a look at another stabilizing motif, which are these aza-azine cruciforms or sigma dimers. So in this motif, 2 aza-azine units are covalently linked by a sigma bond in the center. And of course, there's some literature precedent. So I won't talk about bisantriles, of which there are many derivatives, but I want to highlight this example synthesized in the group of Professor Yishan Wu. And this pentacene sigma dimer, which was the first example, as far as I know, when it comes to a larger acene sigma dimer, showed an increased photostability compared to the TIPS pentacene. And Steffen Meyer, who did the synthetic work, stumbled upon that motif by accident, because what he was really trying to do was to prepare an hexaazaoctazine. And he attempted so by doing a backward-Hartree coupling of the dibromo tetraazapentazine with the naphthalene diamine, which furnished the dihydro species of the hexaazaoctazine. And after oxidation, he was not able to isolate any of the hexaazaoctazine itself, but only of its butterfly dimer in 53%. But also unexpectedly, he observed the formation of this hexaazaoctazine sigma dimer here. And after optical characterization and stability studies, we learned that this hexaazaoctazine, and I think this is the first example of an octazine in the literature, has a phenomenal half-life time of 5 days, of course, in dilute solution. And what happens as a degradation pathway, the tetrahydro species is formed, which can, in principle, and he did that, be reoxidized to act as a reservoir for this octazine dimer here. And why is this half-life so, or why is this compound so stable? This one we learned from the single crystal structure. So you can see that 1/2 of the azine acts as a protecting group for this second half of the azaazine. So the TIPS ethynyl groups protect the center of the molecule here, and the periphery is protected by the wing itself with the 4 TIPS ethynyl groups. And in order to get rid of that undesired reduction pathway, Fabian Jester, and this is unpublished work, tried to synthesize the corresponding tetraazaazine sigma dimers, and he prepared a range ranging from the pentazine sigma dimer over the heptazine sigma dimer to an unprecedented aza-nonazine sigma dimer. And the tetraazaheptazine sigma dimer, this is far more stable than Wan Cheng Zong's diazaheptazine 1, which I talked about earlier. So if you torch it with white light, and the diazaheptazine 1 has a half-life time of 200 minutes in dilute solution, whereas the heptazine sigma dimer synthesized by Fabian retains 95%, around 95% of its absorption intensity. And also the tetraaza-nonazine sigma dimer has a fantastic half-life time of 65 hours, and we believe it to be much more stable than Nicocytus nonazine. Let's move to the last mode of stabilization we had a look at recently, which is substituting the bulky groups on the zigzag edge of the azine with a covalently bound macrocycle protecting the center of the ring. And the idea behind that strategy is simply to physically block oxygen or another azine from approaching the reactive center, and preventing endoperoxide or butterfly dimer formation from happening. And this of course had some inspiration from the literature. So here I brought the example from Kobayashi's group, who synthesized these encapsulated anthrazines with ether linkages of different length. This was the most stable compound he characterized. And Lukas Ahrens in his PhD extended that concept to the pentazines by employing exactly the same synthetic strategy, which consists of Suzuki coupling of a dihalo pentazine to furnish this tetramethoxylated species here, which was deprotected and then subjected to 4-fold etherification with a syringe pump to yield this pentazine jacketed pentazine jacketed by a macrocycle in 30%. Lucas was also able to prepare the corresponding azacenes, and I brought a representative azacene synthesis, which heavily relies on the synthesis of this encapsulated thiadiazole, which is then ring open to liberate the diamine, and then the Buchwald-Hartwig coupling can take place with reoxidation to furnish the tetra-aza-hexacene in this case. And the crystal structure nicely illustrates the constitution of the molecules. By a comparison of the range of azenes or pentacenes and azapentacenes Lucas prepared with their tips ethynolated congeners in exactly the same position as the macrocycle was located, we could deduce that the macrocyclization or protection by a covalently bound macrocycle slightly improves the stability for azacenes, but not much. And unexpectedly, we observed that we made the pentacene stability worse, which was not our goal at all. And why is that the case? We hypothesized that by using these 4 ether groups, we make it 2 electron rich and therefore aid endoperoxide formation, which also is reversible for the TIPS ethynolated species, as Linker and colleagues showed. So we took a step back and had a look again at anthracenes, and that was Philip Ludwig's work. He had a look at different linkers, comprising not only ether linkers of different length and nature, but also at esters. And he also had a look at a different regioisomer, which was a 1,5 substituted anthracene. He was also able to demonstrate, together with our collaboration in the group of Professor List-Kratochwil at Berlin, that some of the derivatives are still active as emitters in LEDs, despite them being shielded. But in any case, he found that indeed the stability correlates with the HOMO energies. The length and the sterics of the linker plays only a minor role, and this 1,5 substituted derivative was interesting because there was some hint at it might provide better stability of the anthracenes. There are other macrocyclic anthracenes around, and this is an example from the group of Sigurd Höger, who synthesized this cyclophenylene encapsulated anthracene with a para linkage between these 2 phenylene groups here. And in a work led by Professor Müllen and carried out by Marvin Natusius, we tried to synthesize a more relaxed, or sterically relaxed regioisomer, which does not have a para connectivity, but rather a meta connectivity here. But we made use of the same beryllium type chemistry as Professor Höger at that point. And we also were lucky because simultaneously to our publication, Professor Höger also reported the exact same compound. Nevertheless, what we learned from that series was that this metaphenylene, this cyclophenylene encapsulated anthracene is far more stable than the than Kobayashi's compound over 1 order of magnitude after artificial aging, meaning irradiation in a photoreactor. And we thought, let's combine these 2 concepts, phenylene shielding and also a diagonal shielding. And that again was part of Philip Ludwig's work, who, to close the loop, took this pentacene tetrone and added lithiated biphenyl and did the subsequent reduction to obtain the tetra-biphenyl substituted pentacene, which also was independently reported by Holger Bettinger's group. And from the crystal structure, we learned that there might be a chance to bridge these compounds here and obtain pentasines which are shielded by quarter phenylene groups. And that was indeed successful. Philip Ludwig did the substitution with chlorinated phenyl groups here, which then were provided the opportunity to do the intramolecular Yamamoto type coupling to obtain the corresponding meta-linked pentasine 1 and the para-linked pentasine 2 as Gelender compounds. The crystal structures illustrate this connectivity here, and the terminology stems from Vögtle's Gelender compound, and Gelender is German for banister, describing the banister of a spiral staircase revolving around the central axis. Again, aging in a photoreactor revealed that the para-pentasine 2 has a tremendous increase in stability with respect to photo degradation, but also to test the resistance towards Diels-Alder reaction. And here you can find an example by Fabian Jester, who degraded or investigated the Diels-Alder addition of PTAD with TIPS pentasine on a preparative scale. We did that with the corresponding sterically shielded pentasines, and we observed that they are far more stable than TIPS pentasine, and even PTAD degrades much faster than these pentasines in solution. So we had to add different equivalents of PTAD at different time intervals to completely degrade these compounds. Another experiments highlights the resistance towards the Diels-Alder reaction, and this is also the reason why TIPS pentasine is not used in bulk heterojunction organic photovoltaic cells together with fullerene as an acceptor, because a Diels-Alder reaction takes place, and in our case, under our conditions, in the course of 1 day, but in the same conditions, pentasine 2, the parashielded derivative, was completely stable. So I'd like to sum up what I wanted to talk about. So if you want to prepare stable azenes and to increase the persistence of these compounds, you crucially have to protect the center of the molecules either by TIPS alkynyl groups, pyrazines, or these acyl substituents. You should not overdo the nitrogen incorporation, and regarding conventional substitution, TIPS ethynyl groups on every second ring work quite well. We do not know what the limit of the TIPS ethynylated sigma dimers are, which kind of act as super TIPS groups. And the glendarization strategy provides the best protection versus the photodegradation and the Diels-Alder reactions, but would be most challenging to continuously implement over the backbone. And with that, I would like to stop by not only thanking the doctoral students which actually did the work, but also a big thank you goes out to my supervisor, Professor Bunz, who gave me the opportunity and the freedom to act as a subgroup leader in his group. I would also like to thank Professor Müllen and also our collaboration partners, which helped in calculations and the OLED fabrication, which I showed you. And of course, financial support was obtained by Uwe Bunz via the SFB 1249 funded by the DFG. And with that, I've come to an end, and I'm happy to answer any questions you might have. Thank you.
Thank you so much, Dr. Freudenberg. That was a great talk, and indeed, some phenomenal results in stabilization. I hand over again to Ilya for questions in the chat.
Thank you, Jean, and thank you, Dr. Freudenberg. It was a great talk. And we have one question from Christian. On the slide 22, he asked, have you tried to use polyol and the metal cation as a template to increase the reaction yield?
No, we indeed have not tried that. We were indeed more than happy with the yields we got, and yeah, so yeah, Lucas always had the hands to work with very tiny amounts, so we did not focus on improving the synthesis for that any further.
Okay, thank you very much. And maybe one question from myself. Have you ever studied any fluorescent properties of other acenes? Because I know that they are used in OLEDs and fluorescent sensors and bioimaging, so just curious.
Yeah, so apart from application in organic light emitting diodes for some anthracenes, aza anthracenes, and some ipticene substituted derivatives, the pentacenes are, depending on their substitution, still fluorescent, red fluorescent, but they have, from what I remember, very low quantum yields. So that was not something we focused on improving.
Understood. Thank you very much. And I think we have one more question from Christian as well. Would it be possible to remove the tips and extend the conjugation of the system with porphyrines, for example?
That indeed would be possible, and I would like to, if I remember correctly, then I would like to refer you to Professor Thieme chemistry, who selectively can functionalize pentacenes and deprotect them on one side and then do further chemistry with that. But that was nothing that we focused on in our group.
Okay, understood. I think there are no more questions, so thank you very much, Dr. Freudenberg, for your talk.
Thank you.
And I forward to Jan.
Thank you again, Dr. Freudenberg, for your great talk. And now we come to the next presentation. And this time, the next two presentations will be by the winners of the Synthesis Best Paper Awards. The first of these two winners will be giving his talk now, and this is Professor Yota Sakakibara. Professor Sakakibara was born in 1995 in Kani, Gifu, Japan. He studied organic chemistry at Nagoya University and received his PhD in March 2022 under Professor Kenichiro Itami. From 2022 to 2023, he was a postdoctoral researcher at Kwansei Gakuin University, where he now serves as an assistant professor in Professor Kei Murakami's group. So I'd like to hand over the floor now to Professor Sakakibara for his presentation.
Yes, thank you very much for kind introduction. I'd like to express my sincere gratitude to the organizers for providing me with the valuable opportunity to present our work today. It's a pleasure to be here to share our recent findings on gamma-selective CH functionalization of tertiary alkyl amines using alpha ammonium radical. Alkyl amines are common structural motif in bioactive molecules. In particular, tertiary alkyl amines are found in approximately 26% of pharmaceuticals and agrochemicals. This high prevalence highlights the importance of developing efficient CH functionalization of these amines. However, achieving such transformation isn't straightforward. As illustrated here with the example aripiprazole, many pharmaceuticals features multiple polar functional groups and a wide variety of CH bonds. These features create a chemically dense environment, making it extremely difficult to functionalize one CH bond without affecting others. And thus, the radio and chemoselective CH functionalization methods has remained a major challenge in modern organic synthesis. This slide summarizes the non-CH functionalization method of tertiary amines. The majority of reported methods focusing on functionalization of alpha position at nitrogen atom. This is mainly because reactive species such as cations, radicals, and anions can be readily generated at this position. Additionally, the CH bond at terminal position of our chain can be selectively functionalized by exploiting steric differences using transition catalyzed boration or oxidation. In contrast, remote and internal CH bonds typically show similar reactivity, making selective functionalization difficult. Nevertheless, the advancement of this area was made by Professor Gaunt and co-workers who reported paradigm-catalyzed gamma-selective aeration of tertiary alkylamines. While this work presents significant progress, it has some limitations. It often requires excess amount of the amine substrate. It's limited to the substrate containing terminal or cyclic gamma CH bond, and the introduced functional group are limited to the allyl group. To overcome these limitations, we devised the following strategy. Firstly, tertiary alkylamine were converted to the halomethyl ammonium salt using dihalomethane. Next, the alpha ammonium radical is generated from halomethyl ammonium salt and undergoes one high fat to translocate the radical to gamma position. This resulting radical is trapped by suitable reagent and following dematuration to yield the corresponding tertiary alkylamines. Given the strong alpha CH bond in ammonium group, we anticipated that alpha ammonium radical can obstruct hydrogen atom from a wide variety of gamma CH bonds. Moreover, due to soap-ingold effect from bulky ammonium group, the intramolecular hat is expected to be fast, minimizing undesired intermolecular side reactions. With this strategy, we found that the ammonium salt derived from dimethyl-butyramine was treated with photocatalysts and TMP under blue light irradiation. The gamma-selective iodide transfer occurred. Our proposed mechanism is shown here. Firstly, the excited state photocatalyst is reduced by TMP to generate highly reducing radical anion. This species reduces iodomethyl ammonium salt to dissociation iodide anion and generate alpha ammonium radical. This alpha ammonium radical undergoes one high path to generate gamma radical, and this radical abstracts iodine atom from another iodomethyl ammonium salt to form product and regenerate alpha ammonium radical, thereby propagating radical chain process. To support our proposed mechanism, we conducted some mechanistic study. Stereo formal quenching experiment reveals that the excited photocatalyst is quenched by TMP. Additionally, the generation of alpha ammonium radical is confirmed by the trapping experiment using tempo. The occurrence of 1,5 hat is revealed through using cyclopropyl containing substrate, which undergoes ring opening reactions, clearly indicating the generation of gamma radical. Moreover, the step in which gamma radical abstract iodine atom from methyl ammonium salt is revealed by the experiment that they are radical and generated under energy transfer mechanism indeed abstract iodine atom from methyl ammonium salts, as shown here. Following the generation of gamma iodinated product, we turned our attention to the subsequent transformations. Firstly, we focus on CS bond formation using cyclohexanthiols. Screening of bases reveals that inorganic bases and TMP were effective, while pyridine and tobacco were not. Interestingly, using the same carbonate not only promotes CS bond formation, but also the maturation of the ammonium group to yield the corresponding tertiary alkyl amine. Encouraged by this result, we performed a one-pot gamma functionalization and dematuration, affording the target product in moderate yield. We applied our one-pot process to various substrates. We found that allyl thiols, including electron donating group or halogen substituent, were applicable for this transformation. Even sterically hindered thiols and naphthyl thiols can be used for this transformation and provide the target product in good yield. In the case of alkyl thiols, primary, secondary, and tertiary examples all gave the target product. On the amine side, substrate including terminal gamma CH bond, branched alkyl chain, and cyclic system were applicable. When using amines including multiple possible functionalized sites, monofunctionalized products were obtained in high selectivity. In relative thiol, amine were viable nucleophiles. By performing firstly SN2 reaction with amine and dematuration with a thiol, we synthesized a wide variety of 1,3-diamine product. In this reaction, various amines including aniline derivatives, primary amines, and secondary amines were applicable. Next, we investigated the reaction between gamma radical with various sulfides. In our previous publication, we demonstrated that methyl ammonium salt can generate alpha ammonium radical via both reductive and oxidative quenching cycle using a photocatalyst. These findings implies that a diverse functionalization are possible by adjusting reaction conditions based on the type of sulfides employed. For example, when the alpha ammonium radical is generated under reductive quenching cycle, the reduced photocatalyst and gamma radical are present. Under these conditions, using electron deficient olefin enables this type of regulation. On the other hand, For mini type reaction using electron deficient heteroaryl compound, the generation of alpha monoradical and oxidative quenching cycle is most suitable. Based on this hypothesis, we examine gamma alkylation and heteroaryl relation. Due to time limitations, the detailed optimization will not be discussed here. However, bromomethyl ammonium salt prove effective for the alkylation, affording the target product in 78% yield. For heteroaryl, using iodomethyl ammonium salt provided the target product in 85% yield. This slide shows the representative substrate scope of alkylation and heteroaryl. For alkylation reaction, not only venous sulfone, but also methyl acrylate, acrylonitriles, and styrene derivatives were applicable. On the amine side, substrate including primary and tertiary gamma CH bond were applicable. When using amines, including two distinctive secondary gamma CH bonds, the reaction occurs at a more electron-rich CH bond. For heteroaryl, a wide variety of heteroaromatic compounds containing isoquinoline, non-derivatives, and benzoyazole were applicable. We then ask whether our strategy can be extended over ammonium salt. Inspired by the unique reactivity of alpha monoradical, we explored analogous alpha phosphonyl and alpha sulfonyl radicals. Both these species have high reactivity due to the neighboring positive charge. By using analogous reaction conditions, we are able to achieve the gamma selective functionalization of phosphorus and sulfur center. Finally, we applied our strategy to late-stage functionalization of complex molecules. Using pharmaceuticals and derivatives containing tertiary alkyl amine moieties, we were able to achieve gamma selective functionalization. This transformation was extremely difficult, if not impossible by existing methods, underscoring the value of our method. In summary, we have developed the new strategy for the gamma selective functionalization of tertiary alkyl amines. Our strategy can introduce various functional groups in high radio selectivity. We have synthesized over 90 examples of gamma functional alkyl amines by using this method. I would acknowledge that this project was conducted the supervision of Professor Murakami, who will be speaking next. I'm also grateful to the student listed here, whose hard working was essential to achievement of this project. I also acknowledge the financial support from these organizations. Thank you very much for your attention.
Thank you so much, Professor Sakakibara. That was a great presentation, and I was very happy to see in one of your early slides that you had referenced your published work in SynOpen. So, thank you. I hand over to Ilya now. Do we have any questions in the chat?
Thank you very much, John, and thank you very much, Professor Sakakibara, for this talk. We don't have any questions, but I wanted just to highlight that it is impressive the amount of variety and the amount of examples that you achieved using this method. I think 19 example is really, really good achievement, and yeah, the chemistry is really interesting, and the results are really incredible. So I thank you for this, and I think we can move to our last speaker, Professor Murakami. Thank you very much once again, Professor Kakibara.
Thank you for listening.
Yes, thank you. And as Professor Sakakibara has mentioned before, our final speaker is Professor Kei Murakami, and he is a winner of the Synthesis Best Paper Award, and he works with Professor Sakakibara. To introduce Professor Murakami, he received his PhD from Kyoto University in 2012. After a JSPS postdoctoral fellowship, he joined the Hakubi Center for Advanced Research and the Department of Chemistry at Kyoto University. In 2014, he moved to Nagoya University as an assistant professor and was promoted to designated associate professor in 2016. Since 2020, he has been an associate professor at Kwansei Gakuin University. His research interests include developing new metal-catalyzed transformations and photocatalytic radical reactions involving nitrogen-containing compounds. So I would like to hand over the floor now to Professor Murakami.
Okay, thank you for your kind introduction. My name is Kei Murakami from Kansai Gakuin University. It is honor for me to present our recent research in this prestigious seminar. Thank you so much. So let me start. Okay. Excuse me. Okay, can you see the slide? Okay.
Yes, we can see it.
Okay, great. So this is a overview of our recent research. So our group is focusing on reaction development, mainly on nitrogen-containing compound. So now I'm in Kansai Gakuin University. Previously, I was in Nagoya University, and at that time, I was mainly focused on aromatic annihilation and CH elimination chemistry. And after that, I moved to Kansai Gakuin University, and now we are focusing on alkyl type nitrogen compound. And also through these developed reaction, we construct a chemical library and to investigate the bioactivity of this molecule. And finally, we found 4 types of new bioactive molecule in our from our molecular library. Okay, let me start. So I'd like to talk about switchable quaternary ammonium diversification. So main contributor of this work is Takumi Kinoshita and Dr. Yota Sakakibara, who presented before earlier. So in our work was published in Chem 2025 and highlighted in cover picture. And so in this work, we developed a new reaction of iodomethyl ammonium salt to generate new radical, kind of underdeveloped radical species to do chemistry. And this work is a switchable reaction, and I like to highlight a related work on switchable transformation. One review is published in ACS Catalysis, and also related work is published in JAX 2024. Okay, let's go into the detail. So quaternary ammonium salt is this one. This is quaternary ammonium salt, which has 4 substituent on nitrogen atom. And this is cationic molecule and used in pharmaceutical and catalyst. So these molecules have been known since like 19th century. So it is very classical molecule, but synthetically less explored. So for the synthesis of quaternary ammonium salt is summarized here. So mainly, most of all quaternary ammonium salt is prepared by Menschetken reaction, which is known as tertiary amine alkylation. And in 2018, this reaction is applied to the reaction of benzene. So in which triazolamine reacted with benzene to give this aryl ammonium salts. And in 2021, Professor Kitchen reported enantiomer selective synthesis of this quaternary ammonium salt using binol. And meanwhile, these are kind of Manchester type reaction, and other unpolling approach is also reported by Professor Tobias Ritter in Nature Chemistry 2016, where selectofluor reacted with a real arene in the presence of palladium catalysis to give this one. However, most of all syntheses are based on Manchester reaction. So it is very important and it is good to access these ammonium salts through Manchester reaction. However, if you want to access a wide variety of ammonium salts, you need to do develop a new diversification reaction of quaternary ammonium salt. But these kind of reactions remains elusive. So this is related important work on ammonium salt transformation. So Professor Phipps reported benzyl ammonium salts treated with reacted with this type of iridium catalysis to do metal selective boration to give this one. So this is an important part of ammonium chemistry to accomplish ammonium transformation. So to develop a novel ammonium transformation reaction, our group are focusing on this alpha ammonia radical. So, however, this is kind of underdeveloped species. So in 1999, Professor Smith reported intramolecular reaction. So starting from this iodomethyl ammonium salt to generate radical here and do cyclization to synthesize this kind of molecule. So this is successful intramolecular type reaction. However, intermolecular reaction was mainly unsuccessful. So provided a compound in low yields or low selectivity. And after 20 years, recently these chemistry have been highlighted. So in 2023, Professor Gevorgen reported a 3-component palladium catalyzed reaction using this one, bromomethyl trimethyl ammonium salt as a linchpin to make these type of allyl amine species. So in this reaction, the starting bromomethyl ammonium salt are activated by reacted with palladium 0 under blue light irradiation to give this alpha ammonia radical. And this radical can do radical mediated Mizuloki-Heck type reaction with styrene to give this one. And this allylic ammonium salt can do Tsuji-Trust reaction using palladium catalysis to give this one. And at the same time, our project started from 2021, and we developed a new reaction using this radical under photoredox catalyzed system. So under oxidative quenching conditions, this one generated with photoredox catalysis and react with alkene to give cationic intermediate, which can react with base or various nucleophiles to give these molecules. On the other hand, under reductive quenching cycle, this radical can react with alkene to generate this anionic species so that they can protonate or deuterate it to give these molecules. Okay, let's go into the detail. So this is a catalytic calculation, alkynylation reaction. So starting from iodomethyl ammonium salt with diphenyl ethylene in the presence of iridium PC for the redox catalysis with silver BF4 salt in DMSO and blue light irradiation for 2 hours afforded this compound allylic ammonium salt 3A in 78% yield. So this is the scope of the reaction. So not only trimethyl 1, but also triethyl or isopropyl dimethyl or pyrrolidine or molphyline type or cyclic ammonium salt can be employed to this reaction to give this compound in moderate to good yield. For diaryloethene, various substitutions, for example, methyl or methoxy halogen can be tolerated under the condition to give the compound. And not only diphenyl, but also stereotype compound can give this compound, this product in 34% yield. and EC ratio is 90:81. And so mainly Z-type compound was obtained. So here you can see the mechanism of this alkylation. So starting from photoredox, which is activated by blue light, and this catalyst reduced iodomethyl ammonium salts to give alpha ammonium radical here, and this react with diphenylethylene to give this benzylic radical B, and then this is oxidized by PC to give 3A through deprotonation. And this reaction mechanism was confirmed by quenching experiment, Stern-Fulmer experiment, and nicely showed that the excited photocatalysis is quenched with 1A. And also the resulting radical A was trapped by tempo derivative, and this was isolated. So using different reaction condition, we can obtain alkylated product from the same starting materials. So under the in the presence of PC2 with triethylamine as a reductant and blue light irradiation for 2 hours to give 4A in 73% yield. And the scope of this reaction is as broad as the previous alkylation reaction, and various compounds can be obtained in moderate to good yields. So here is a mechanism of this alkylation reaction. So starting from PC2 blue light irradiation to give activated PC2, and this was oxidized. This oxidized triethylamine to give alpha radical here, and this can abstract iodine here to give this one, and at the same time generating alpha ammonium radical. So this is XAT reagent and reported by Professor Leonori in Science 2020. And the resulting radical can react with diphenylethylene to give intermediate B, and then this is reduced by PC radical anion to give 4A. And the reaction mechanism was also confirmed by quenching experiment as well as radical trapping experiments. So optimized and very efficient reaction condition in hand, we did applicational switchable alkylation and alkylation. So with a condition A, like a beta ammonium radical can react with diphenylethylene, or bioactive one or strychnine derivative can be alkylated, or diammonium salts also can be alkylated to give these compound in moderate to good yield. Under the condition B, reductive condition, we can obtain the corresponding alkylated product. So this is very important. If you use Mann-Schutkin reaction at the final stage to synthesize this molecule, you need to prepare 2 different halogenated alkyl halides. However, in this condition, we can start from the same starting material and changing different reaction condition, and we can obtain different compounds. So this is very efficient to access a wide variety of compounds. So let me show the synthetic application. So when you start from this triethyl one with phenyl cyclohexylalkene under oxidative quenching condition, in situ generating cation can be quenched, trapped with water, which we added in the system. And we obtained tridihexethyl. This is bioactive compound in 53% yield. And because this is cationic intermediate, if you add methanol as a nucleophile, you can obtain a methylated compound in 50% yield. And also using other nucleophile, you can easily derivatize tridihexethyl in different structure. And also using ammonium salt is advantageous on making deuterated compounds. So this proton is very acidic, so that treatment of this compound with sodium hydroxide in deuteriol, we can easily obtain this deuterated iodomethylammonium salt. And under the oxidative quenching conditions, we can easily obtain deuterated tridihexethyl. And similarly, deuterated ammonium salts can do transformation under reductive quenching condition to give this one, and demethylation using this condition allows you to give this one in 50% yield. So this is a very good review, importance of deuterium in drug discovery, summarized in Nature Review Drug Discovery 2023. So please check this for the importance of these molecules. Alkylation and iodomethylation to give this one. And then you can do similar chemistry so that generating radical here and cyclize and react with diphenylethylene to do alkylation sequence to give this one in 63% yield. And under the reductive condition, you can obtain a cyclization alkylation product in 57% synthesis of alpha alkylated alkynyl ammonium salts. So this was selected as synthesis best paper hours. Thank you so much. We appreciate it. And we sincerely appreciate Professor Mark Lawtens and the editors and the team for selecting and highlighting our work as a Best Paper Award. And in the comment of Professor Mark Lawtens, ammonium salts are a somewhat forgotten group to carry through many classes of reactions. Murakami and our group is changing that perspective with this excellent contribution. So it was very honor for us to receive such a great comments. So thank you so much. And this is the team of this paper. So main contributor is Rina and Aoi and Yota. So the reaction is this one. So previously we utilized iodomethyl ammonium salt, but instead we resulting radical can react with diaryloethene to give the corresponding product in good yield. So the scope of the reaction is similar as the previous one. So you can use various diaryloethene, and also for ammonium structure, various much bulkier one or cyclic one can be also used. And here you can see the reaction mechanism of this reaction. So this is similar to the previous alkylation reaction. So photocatalysis is excited by blue light irradiation to give this one, and this one oxidized amine to give this one, and also generating alkynyl radical D. And this is very reactive radical, which can be trapped by diphenylethene to give this one, and single electron transfer to give this anion, and then protonated to give this one. So this XAT reagent is developed by Macmillan, and which reported in JACS in 2020. So for reaction mechanism, the generating anionic species was D2O to give this one, and more than 99% D. And the product can be apply or diversify to another product. So under hydrogenation condition, catalytic reduction to give this one, or using Dabico as a demethylation reagent to give this enamine, and which transform to this material, we can obtain enamine. It means this is a nucleophilic intermediate, which can react with benzaldehyde to give this one, and finally dehydration to give this one in 79% yield. So this is kind of radial selective enamine generation and can be applied to further chemistry. So move on to the next topic. So how to functionalize gamma position selectively, and you might so our answer is using alpha ammonia radical, and this can abstract hydrogen here to generate radical here. And this is linked to Chem Archive. And if you want to see the detail, please go to check Dr. Sakakibara's presentation from the archive provided by Thieme. I'd like briefly introduce overview of this work. And so starting from tertiary amine, and it is quite, and do photoredox catalyzed chemistry to abstract here to generate radical here, and then we can do sulfurage. We can install sulfur moiety or alkylation or amination. So now we have more than 90 examples, and we are submitted to Chem Archive and submitted to our journal. Okay, the final topic is harnessing methodology development and plant chemical biology. So in reaction, more than 90 examples. So typically, once a paper is accepted, the synthesized compounds are stored in a freezer and remain unused, maybe forever. However, when we examine these compounds, we realize that although they are synthesized, the building blocks used in their construction differ, so making them a structurally diverse set of molecules. And moreover, it is important that these molecules are basically unknown molecules, so bioactivity is also not investigated. So based on this idea, we decided to investigate the bioactivity of these molecules, hidden bioactivity of these molecules. And now my group is collaborating with more than 10 biologists. So, because of time limitation, I will not able to discuss the detail of all topic today. So, but I'd like to highlight these three molecules. So this is when we did Thieme Chemistry reported in Chem 2017, we constructed chemical library and we investigated the bioactivity of these molecules, and we finally found new bioactivity from our new compounds. And this strategy is applied to other collaboration chemistry and unexpectedly obtained this compound. But this is the first small reducing molecule. So this is so exciting. We found a new reaction. This chemistry, please check our website, or you can see the detail in NatureCom 2024. And we developed this NCS substituted xylene molecule, and this is a strong small opening, so we can confer drought tolerance to plants. So I will show you the video. This is flowers placed in a vase without any water, no water here. So let you see the slides. So now you can see flowers is wilting. So as a result, the untreated flowers begin to wilt quickly. In contrast, the flower treated with this compound we named BITC remain BITC successfully enhanced drought tolerance in plants. So using 50 micromolar, still the flower is fresh. And from this strategy, we found a new bioactive molecule from our ammonium salt library. So this is salinity tolerance conferring molecule we named attack 131 or 141. This is the photo here on the right shows seeds here, very small one. Seeds sown in a salt-containing medium, about 100 millimolar NaCl medium. And it is well known that plant growth is significantly inhibited in saline environment. However, when our molecule here was introduced, plant growth was noticeably promoted. So please compare with this one without molecule and this one with our molecule. So we found activity in the nanomolar range. So what is the significance of this research? So currently, the global food crisis is a major challenge. It is by 2030, it is estimated that 800 drought are among the most significant. So it is predicted that by 2050 here, 50% of agricultural land will be affected by salinity. Additionally, due to global warming, by 2050, 75% of the world population is expected to suffer from water scarcity. And even today, 2.3 billion people are suffering from water loss and drought tolerance in plants. And of course, these findings alone will not solve all problems, but we hope that this molecule will serve as valuable tools in very fundamental plant chemistry, plant science research, and contribute to addressing these the global food crisis. Okay, this concludes my lecture. The series of studies was made possible. I'd also like to thank express my gratitude to the Japanese funding agency and supported our research. So finally, I sincerely appreciate the organizer for giving me this wonderful opportunity. Thank you so much.
Thank you so much, Professor Murakami. That was really, really engaging, and I want to thank you for that. We have a good number of questions in the chat, so I will ask Ilya to help moderate, please.
Thank you, Jean, and thank you, Professor Murakami. It was a wonderful talk, both chemistry and biological aspect. Why occur at carbon iodine bond instead of carbon nitrogen bond, and how you isolate the pure product.
Okay, so question made. Oh, excuse me. This one. Maybe question is this one, cleaving CI bond, not CN bond.
Yes.
Yes. Okay. So because the ammonium salt triacylamine moiety is not so good leaving group, so that CI bond easily cleave to give this radical. And for the purification, we did various way to isolate these compounds. So we sometimes use silica gel column or recrystallization or both. So, but mainly because thanks to students' efforts, we can obtain these compounds.
Would it be possible to control, from Christian, would it be possible to control the easy ratio?
Maybe this one. Monitor the reaction by NMR, and firstly, E isomer difficult to how to say isolate this as a pure form, and E or Z form.
Okay, perfect. Thank you. And the next one is Bo Huen Ru. I hope I'm pronouncing right. Excuse me if not. Is the question? He's wondering whether you can use your allele ammonium product.
Develop a new reaction, and hope to see you. Hope we can publish it as soon as possible. So
triethyl amine. Why does the carbon radical of ammonium react selectively with alkene? Why not react with carbon radical of triethylamine?
For this one, why this not react with this one, but this one? The reaction of ammonium salt is faster, maybe because this is more reactive, but I'm sorry, we don't have any like a quantitative data to explain why this is faster.
Okay. I think we can move on. If there are any following questions, they can be asked in the chat. Then
I think we've never tried. We only use D2O or yeah.
Okay.
Now we are investigating these testing these compounds. Basically they didn't show any like a toxicity. Mainly plant grows very healthy.
Okay. Thank you. And the last question in the chat from Swastik Bisos. Did you try to trap ammonium radical with alkyne or strain rinse system?
Not tried, but it will be very interesting, so we will try. Thank you.
Okay, thank you for the questions.
Which reaction? For the first one?
Yeah, the first one.
So for styrene, so this is the...
Okay, thank you. Then I think there are no more questions, and Jean, you can take over. And once again, thank you, Professor Murakami, for this wonderful talk.
Thank you, Ilya, and thank you to everyone for all your questions. And please join me once again in thanking our speakers for their excellent presentations, Professor Sung-Kyu Han, Dr. Jan Freudenberg, Dr. Yota Sakakibara, and Professor Kei Murakami. I'm delighted to be chaired by Synthesis Associate Editor, Professor Xinyuan Liu. In August, we will have a seminar dedicated to Professor Eric Carrera and his work, to be chaired by Synthesis Editor-in-Chief, Professor Mark Lautens. And we will have one more, Olivier. So thank you so much for joining us today, and I look forward to seeing you again at a future seminar. Have a great rest of your day, and until next time.